Okay, thanks first for the invitation. So in this talk, I will address neural networks, deep learning frameworks for dynamical system, and provide you some insights on this, and with a specific focus on using those techniques for partially observed systems. So maybe first I have one question to know who in the audience has some background in neural networks and deep learning, and who has not. So who has some background in neural nets? Let's say like 25%. Okay, good. Okay, maybe first some background in our interest from, so we are mainly, in terms of application fields, we mainly address or develop techniques, data-driven techniques approaches for ocean monitoring. So especially regarding the use of satellite-derived observation for the modeling, reconstruction of upper ocean dynamics. Okay, and one point in satellite-derived sea surface observation, I illustrate here a number of different observations. You may know some of them. And the key point here is that all these observations involve irregularly sampled observation, meaning that you may have high resolution in space, but not in time. You may observe only tracks on the sea surface, or real swath, or real images, or patches. Or you may be some sensors are sensitive to the cloud cover, like for the SST here, this example. So we have this kind of observation, and what we'd like to do is to truly use all this all those data to learn representation of ocean dynamics directly from those observations. So meaning we have to deal with those partially observed or irregularly sampled or irregularly sampling of a system, and like to train from those data sets. Okay, so this is our basic interest, and the key point here is to know how we can use data-driven techniques, learning-based frameworks to solve those sampling gaps and to get some kind of representation of the underlying dynamics. And I'll give you some ideas of some work we are developing on this. So before going to the neural networks, maybe some background on what we've done before, and giving you some explanation of why we're moving to neural networks. So a few years ago, or we're still looking at this, we developed ideas on analog forecasting techniques applied to data assimilation. So we refer to this as analog data assimilation. And the idea is to basically combine analog techniques to state-of-the-art data assimilation scheme, especially ensemble CAM techniques. And we've shown we can combine those schemes to get data-driven data assimilation techniques. Okay? And here I refer to different example where we applied this to sea surface observation, for example, for SST interpolation, for the reconstruction of sea surface currents from altimeter data, where we get quite good results. The key thing here is that we do not learn from the observation. We analyze the observation using the analog techniques, but we need some reference data set. And the data set is provided by high resolution numerical simulations. Okay? So we need some high resolution reference data to be able to use the analog techniques. So I haven't explained what's the analog techniques, but basically the idea of the analog forecasting operator is given a reference data set for a current state. You look for similar situations in your reference data set. And in the reference data set, you know the future of those similar states. So you can predict the future of the current state from the future of similar examples in your reference data set. So here, the open question somehow when considering analog techniques is to know how to bridge or how to bring physical knowledge in those analog techniques. and also how to learn data representation from real observation data set. And it's rather unclear how to consider analog techniques to answer those two questions. So that's why we moved to neural networks. And you probably all heard about neural networks with this idea of black boxes where you don't know anything of what's done inside the box. And the idea here will be to move to white boxes, meaning neural networks in which you truly know what's inside the box. I explain this and right now. So maybe I go to this directly. So there is a class of neural networks where you can have this link between ODE or PDE representation and neural networks. Neural networks are, in that case, just some kind of numerical solvers of the ODE or the PDE. So here, one very simple example. If you consider the heat equation here, and you consider a very simple Euler scheme for solving this PDE, you will come to this kind of representation, where the U at time t plus 1 will be U at time t plus a residual, which relates to the application of a Laplacian operator to the current state. And you just sum. This kind of neural network is called in the machine learning community a residual neural network. You can extend this, and it's called ResNet. Okay, the machine learning guys love to provide new names to any kind of architecture. So this one is called ResNet. So now you can see any.
It's just a four-point Laplacian.
Yeah, in that case, meaning is this useful? Probably not directly that way. But imagine now you're not sure that but your diffusion is truly Laplacian diffusion. But you assume there is some kind of diffusion operator existing. So now you could provide some parameterization for the diffusion operator, not necessarily the four-point Laplacian operator. And now if you have a data for the state at time t and t plus 1, you can learn the parameter of the diffusion operator. That's where so if you have some kind of knowledge of the kind of operator involved, you can bring this here. You can also extend this to Runge-Kutta integration scheme. Any kind of explicit integration scheme can be used to design some kind of neural network architecture. So one example here, we applied this idea to Lorentz 63 dynamics, where we design a neural network architecture for which we know that one solution of this architecture in terms of parameterization truly refers to the parameterization of a Lorentz 63 dynamics. Okay? And now we provide data, so a numerical simulation of a Lorentz 63 dynamics, and we look whether or not we can recover good simulation performance, forecast performance, when we train the network from the data. And so that's the last one here. And here we use a Runge-Kutta fourth order for the network. And we compare this to a number of other data-driven techniques. Here, because the network is fully consistent with the simulation, we get very good performance in terms of forecasting. The important thing here, if you consider another kind of network, MLP, which is a very standard network, which doesn't use any kind of information on the structure of a problem. So in that case, the network has doesn't implement an integration scheme. You may have very bad or much worse forecasting performance. Meaning that depending on the kind of neural network architecture you consider, you'll have very different kind of performance. So in that case here, I'll only deal with, so for the learning part, the data set I used for the Lorentz 63 dynamics was a perfect data set, meaning consider I have all the states at very high resolution in time so that I could use directly the learning idea. So now, what if I have to deal with partially observed systems or noisy ones? So we have considered different cases on this. We have considered the case where you have observation of the true states, but so with a scarce sampling in time. For example, for the ocean would be, imagine you have high resolution observations, but only every week, okay? So you don't have the daily information or sub-daily information. You have only the information every week. So we've shown you can, in that case, jointly learn the numerical integration scheme and the ODE operator. Another case, I may detail, I'm not sure, depending on time, is a case where you have some irregular sampling of your observation. So that's really the case of satellite-derived observation at sea surface, like sea surface temperature, altimeter data, where you sample some points on sea surface, but not all points. So in that case, we have, I may come back on this later on, and I will focus on this case here. Okay, when you consider the upper ocean dynamics, the satellite will provide only information, observation for the sea surface. So you have no observation from the satellite for the information at a given depth. Okay, you only see the sea surface. And obviously, the dynamics of the sea surface depends on what's below the surface. Okay, so you're in the situation where we'd like to train or learn a representation, an ODE representation for the dynamics of the sea surface, but we know, but we only have the information of the sea surface. So how to learn this? Generally speaking, the idea for this will relate to a joint identification and reconstruction issue. So we'll define a representation that will be an ODE-based representation. And to be able to learn the representation, we will need first to reconstruct a latent state, so an unknown state. And to do this, we need to use some assimilation techniques, so some kind of inversion technique. And basically, the idea will be to iterate the identification of the operator and the reconstruction, assimilation step. So, and our goal is, so there may be a number of different options, both for the operator, the identification step. So obviously, as presented before, I'll use a neural network for this. And for the inference step, for the assimilation step, I may use state-of-the-art assimilation techniques, for example, stochastic filtering, ensemble Kalman techniques, 4D VAR, for example. Here, what we'd like to do is to design an entire network combining within the global neural network architecture both the identification model and the assimilation model, okay? And we'd like to be able to train both the identification part, so the ODE operator, and the assimilation part. Okay, so I explain this a bit more for the partially observed case. So as a case study or a toy example, I consider Lohan 63 dynamics. And I assume here I only see, I have only observation for the first component, okay? So basically I have a time series like this. And I know that this relates to a three-dimensional state. I never observe the second and third component of the state, okay? Never. I'd like to know whether I could identify an ODE representation. Here, the variable would be z, which allows me to predict the evolution of the observed variable, here x1. Obviously, the dimension of the state z should be at least three dimensions, okay? My state z, the latent state, should be at least three-dimensional. There is no way to find an ODE in a one-dimensional or two-dimensional space, allowing me to reproduce the evolution of the observed first component of Lorentz distribution dynamics. Okay? Because in the Lorentz distribution dynamics, the three states are coupled. Okay? So here the idea, so to solve this, in the literature, classic ideas are to use delay embeddings. So the way you build your latent state is basically that you stack observation in the past over a given period, over a given delay, okay? And then you train a model in this delay embedding space. Here, what we'd like to do is only to, we don't want to use delay embeddings. We only like to use, the only thing we'd like to state is the parameterization of the ODE. So we come to this state space model where the latent state has some observed part, so the observed variable, in our case x1, and we add additional dimensions where we only set the number of latent dimensions. So here it could be 2, 3, 4, 5. And we state that in this latent space, there is an ODE stating the evolution of a state. And here we choose a specific parameterization. So we consider a class of possible ODEs. For example, using polynomial expansion, so we consider a class of ODEs. And the goal here is to train parameter theta, so to train or to identify the specific parameterization and the class of ODE considered, just from the time series of the observed variables. And given this, we will apply this to the simulation of new time series, given just, again, the observation part. So this, the way we state this, we basically, it's somehow very, it's just a standard state space model problem statement, and we use a variational formulation. So basically, the estimation, the identification of a theta relates to the minimization of, with two terms, one which is just the ability of a model to predict the evolution of the observed variable, and the other term is basically the consistency of the dynamics of the latent states with respect to the trained ODE. So, and all we have to, so what we'd like to train here, or to identify are the parameters theta, and to train theta, we need to reconstruct the unobserved part of the latent state. And we solve this directly within the neural network framework, because we have, through the, those frameworks, we have access to the numerical adjoint of all the operators. So we can directly solve for this minimization using a classic gradient descent, just at once, and solving for directly, jointly for theta and the latent states. So example here, I move, wait, or maybe, yeah.
Sorry, can I just also,
yeah.
Capital X there in this case will have dimension 3, right? No?
At least 3, yeah. Capital X is 3, yeah.
So in a way you are observing all this, right?
No. Here it's capital X, here it's small x. Okay, and J is the operator to move from the capital X to small x, just to get the observed part of the capital X. Okay? We know J here, which is just the selection of the observed part in the capital X, which is the full vector. Projection. Yeah, it's a very simple projection, nothing to learn. Okay? Yeah.
And then the capital X, how do you compute the capital X?
All you know for capital X is this, is that you know the observed part of capital X, so here the first dimension, and you don't know the two overts, for example, if it's three-dimensional, and you're gonna solve for the identification of those latent states from this minimization. So basically, you look for the best latent states and the best parameterization of the ODE jointly.
Sorry, latent is hidden?
Yeah, yeah,
Okay,
yeah, sorry.
Just a different word.
Yeah, yeah, exactly.
To make it easy.
Yeah. Okay, here are an application to the Lorentz 63 case with a number of comparisons with delay embedding or techniques based on delay embedding using analog forecasting or sparse regression. And here comparison to ODE or neural ODE frameworks or neural networks where you also use this idea of delay embedding. And here the proposed approach. Two things. We evaluate the performance in terms of short-term forecasting error. And look at this here. We have some order of magnitude of difference. So we have a much better precision when using the proposed approach. And depending on here, we also get a quite good estimation of a largest Lyapunov exponent. So meaning that for the long-term behavior of the system, we also have a good estimate of the long-term behavior of the system. So not only on the short term. Whereas we train the system only from short-term forecasting errors. And we think that really relates to the fact that we only set the ODE and we never use the delay embedding idea, which is a way to constrain the optimization and might not be the best way to do this. Here, an idea of the kind of, so the evolution of a latent state from the beginning, where we just use a random initialization, to the end, where you get something which is topological speaking similar to the Lorentz 63 attractor, which is what we expect. Okay, here, so the same kind of, we apply the same kind of thing in a reduced order modeling case to SLA data. And here, a comparison of a forecasting performance for one example of a proposal approach compared to analog forecasting. And again, here you have the comparison between for an animation for the true system. Here it's the analog forecasting, and here it's the proposed approach. And you see that here the analog forecasting may diverge, okay? There is no, because basically the system is trained somehow, including for analog, only for short term. You have no guarantee that for the long term, you keep something consistent. Whereas it seems, at least for about 200 days here, that the ODE-based framework using neural networks seem to be better in getting a more consistent time evolution for long term. I may have not time really for this. Just here, I won't detail this, that I never mentioned, and we never used any kind of constraint in the previous slide on the stability of the system, or the expected stability of the system, or on the existence of trapping region for the attractor. We may also embed this or constrain this in the learning. So there are ways, because we truly use an ODE, we may constrain the stability. It will may add an additional term in the minimization, basically. So it's rather simple, and we can truly constrain this. Here it's an example where, using this, we truly enlarge the region of convergence towards the attractor, depending on the initial condition. Okay, I skip this. Maybe a conclusion and a summary. So the idea of using neural nets is basically to look at neural nets as numerical schemes for the implementation of ODEs, PDEs, or any kind of physics-informed representation. Okay? So the neural net is just the computational tool, not the theoretical one. Okay? We still have all the theory from ODEs, PDE, or any kind of other kinds of representation. That way you may embed in the neural network architecture different kinds of knowledge on the physics. Could be the parameterization, could be stability priors, energy conservation priors. That way you have what's called the end-to-end architecture, meaning you can have, rather than calibrating in sub-boxes or sub-models for a specific task, you directly consider your input and output for a given task. In that case, the sea surface observation, and I train all the sub-models at once from this observation. And here I haven't mentioned extension to stochastic representation, but you can do so. Olivier, this afternoon we'll give some brief insights on this. We have a number of other illustrations for this. Okay, thanks. Yeah. No, not the last one. Yeah. Yeah. So more details on preprints on our webpage, and obviously this is a joint work with a number of people, including some in the room.
Yeah.
So thanks for this very good talk. So I have two questions. There is a you talked about stochastic representation in the last slide. So what do you mean exactly? And so another question is, you never talked about the amount of data you need to have in order to learn a model of a given complexity. For instance, the thing that you have proven to work very well for the Lorentz 63 model, how much data would you need to have to learn something bigger? So for instance, a partial differential equation for the sea surface temperature or something like that.
Okay, maybe the second one first. It's the same as in any statistical problem. Basically, the number of data you need relates to the complexity of a model. Okay, so it really relates to the parameterization you consider in the neural network. So for the Lorentz 63, for example, you can consider typically the kind of architecture we design involves up to a few tenths of parameters. Okay, so you'd expect not to need like billions of data. And for the experiments I've shown you, we use a time series of 4,000 steps. And it seems to behave quite well from a few thousands up to more, obviously. And if you increase the number of data, you get probably something more stable, and you're even more precise in terms of forecasting behavior. So now, if you consider now for a given system, for example, for sea surface temperature, if you have no ideas on the parameterization of the operator, then you may just consider a standard CNN, and then you may go up to 1 million or more, a few millions of parameters. Okay? So in that case, obviously, you need more data. But basically, the range would be from a few hundred to a few thousands of scenes, so images in that case. So not billions, even in that case. And the second one was a stochastic thing. Okay, in the different talks this morning, the SODE or SPDs involve some kind of parameterization of a stochastic component. For example, some kind of polynomial expansion in a broad sense. So there are a class of networks where the output of a network are the parameters of a distribution. So the only thing you can, so meaning the output is not a state, but the output is are the parameters of a distribution. So if you consider a Gaussian prior, for example, the output of a network would be the mean and the covariance, for example. And you can extend this to any kind of parametric form of a distribution. You may even think about, yeah, If you have a covariance-based approach, for example, you will change the least square function to something involving the covariance. So you move to some kind of likelihood-based function. This is very simple if the parametric form of a distribution can be decomposed according to the elementary operator available in the deep learning frameworks. So that's more or less the idea. So you can, I mean, all the theory should come from statistical modeling, and then you try to plug this within a neural network framework.
Sorry, coming back to that very simple question at the beginning. So you said, well, it's not the 4-point Laplacian. You tell it that it's a diffusion operator.
Yeah.
How do you tell it that it's a diffusion operator? I mean, you know, anything that's different from the 4-point Laplacian or the 9-point Laplacian, whatever, is going to be a reaction diffusion or advection diffusion kind of operator. So what do you tell your network? I mean, as opposed to doing any sort of connections.
Okay. You may constrain. Okay, if you consider a linear filter, okay, maybe first, and you'd like the filter to behave as a diffusion filter, you may add constraint on the symmetry of the filter, for example. So the first would be just to train a filter where you just set the size of the filter. Let's say 3 by 3, 4 by 4, 9 by 9, 11, whatever. And you let the system train all the coefficients of the filter. Okay? In that case, you'll get a filter, but the filter might not be what you expect from a diffusion filter. For example, if there is no symmetry, or if you expect some kind of isotropy, then you may enforce this using additional constraint. And it would do the same. In the cost function you minimize, you'll add terms with those constraints. That's one way to do this. Another way is to reconsider a parametric form of the filter where you ensure this isotropy, for example. So, or you have a class of parametric representation of interest, and you set this, enforcing all your expected constraint, which is not feasible or available at any time, or you implicitly constrain this through the cost function, which is often much easier. And then the constraint or the guarantee you have is only up to the ability of truly minimizing according to those constraints.
Okay, any last question for Ronan? Nope, okay. So thank you very much, Ronan.